Just give me un momento. So I figured out a better way to do the recording thing instead of having Teams. So the way that it should be recorded is exactly how you see it right now. It's smoother, the audio quality should be better. So hopefully this is sufficient. I just need to figure out how to throw everything. So how was everyone's first week of classes? They liking their classes so far? Kind of sucked? Yeah. Why? Oh yeah, you missed this class, but that's fine. You know, there was a lot of hiccups.
Hiking everywhere.
I'm so sorry.
You're good.
Let's what's that? There we go. Yes. All right. What's everyone's favorite class so far? Excluding this one. You know, since I know everyone loves this class.
The Revit one.
Revit?
Yeah.
I never took Revit.
Really?
Yeah, no. I switched my major before I took Revit. But
That's so fun.
Revit's very useful. I wish I took the course because I don't necessarily use it, but I know people who use it a lot in industry. What about other classes? What else is everyone taking?
I like estimating.
Estimating?
Yeah.
Taking that with Dawson, right?
Yes.
Yeah. Just wish before I took that. I got out of that. Structural drafting. Anyone doing that right now?
Next semester.
Next semester? Oh, that's a fun one. Residential drafting? Or did you guys do that one already? Did that one? I didn't like that one.
Why?
Professor Neiman would like nitpick everything.
Wait, which one?
Residential?
No, but like Kirk or Natalie?
Neiman. Wait, hold on. They're both.
Girl.
Professor Natalie Neiman. Yeah, I forget. I only just met Kirk last semester. One of my favorites was site planning. That was a fun one.
We have that one. Yeah.
No? Really?
We got
Dang. That was a fun one. It taught you how to design like roadways and such, you know, which then when I went to a Stony Brook, I had to relearn it and the professor sucked. So that professor is the reason why I hate transportation engineering with an absolute passion. Professor Dawson would be so disappointed in me for saying that since he's a transportation engineer. All right. So let's get straight into this lecture then. So today we are learning some new topics. We are learning about the concept of stress. Now, who here knows what stress is? What do you think of when you hear the word stress?
pressure.
Pressure. All right. What else?
Wait, no, that's something else.
What did you say?
I was gonna say strain, but that's something
Strain?
else.
Strain, you said?
Yeah.
Strain is related. We're actually going to get into strain next week, which has to do with deformation in materials.
Tension.
Tension? Well, that's a type of force. So stresses and forces are entirely two related things. They're two separate things, but they are related. So stress is what we use to design things, right? Let's say that we've got a beam. Let me actually do something different. Let me remove that. Let's say that we've got some type of column here. And it's loaded with, I don't know, 200 kips of force. Now, we know that we can determine all of the reaction forces within the member. For this one, it's going to be pretty straightforward. The only reaction force is just going to be 200 kips vertically upwards, right? Make sense? Great. How do we know what size the member needs to be? We don't, right? So, stress is a normalized unit of force. That's not English. And it's used to evaluate load carrying capacity of members of different sizes. Right. Let's take, for example, a concrete beam, or no, concrete column. What do you guys think is going to be able to handle more load? A 12-inch by 12-inch column or an 18 by 18-inch column?
18 by 18.
Why?
It's bigger.
It's larger. Now, you guys know how concrete is defined by a type of compressive strength. Like you guys might have learned from, what is that course that Simon teaches? What? No, it's like the very beginning. Construction methods. You guys learned about how concrete can have different strengths. For example, 4,000 psi concrete, 5,000 psi concrete. What does that mean? Exactly. It's the pressure that it can handle or the force that it can handle per unit area. So now let me ask this. Let's say that 12-inch by 12-inch column was 4,000 psi concrete. No, 8,000 psi concrete. But the 18 by 18 was 4,000 psi concrete. What can handle more load now?
That's what my small.
Well, how do you know?
Because we need to take more load bearing.
Yeah, but the 18 by 18 has a larger area. So you need to do the math in order to determine it. But this gives us an idea. You know, the compressive strength is defined as a force over some type of area. So that's what stress actually is. It's force per area. And it's as simple as that. All right, end of the class. I'm kidding. Don't leave, please. So when we are determining a stress within a particular member, we take whatever load it is, and then we determine it, what the stress is within the member by knowing what its geometric properties are. We can have different types of stresses. Different kinds. We can have, what do you guys think are some type of stresses? Like, think of like different loads that you learned about in statics. What are different forces that you guys learned about might be acting on a building?
Horizontal and vertical.
Yes. So you have vertical forces and horizontal forces. Vertical forces might be loads like this acting in column, right? Yeah.
Like dead loads?
Dead loads are a type of load, yes. Yeah.
Wind?
Yes. So all of these loads can be generalized into various different kinds of loads. So in the case of like a column being loaded like this, we would call this axial loading or axial stresses. And what this basically just refers to is simple tension and compression. We can also have shear stresses. Who here knows what shearing is? Anyone? Anyone want to take a crack at it? Shearing. Anyone who here has not heard of the term shear? Everyone's heard of the term shear. But what is it? It's sliding.
Yeah.
They're sliding stresses. We'll actually learn about shear stresses next class. We can also have bearing stresses. What type of structure do you think might transfer bearing stresses?
Girders,
Yes and no. It depends on how it's ultimately connected. I'd say a perfect example of this would be like footings, where there's a straight contact area in which something's pushing down on. So I'm going to put like footings, for example. We can have bending stresses. What type of structures do you think undergo bending stresses?
bridges,
Bridges, yeah. But bridges can take, what part of a bridge specifically though? Because bridges can take pretty much every single type of these. It's just a structure. The particular elements themselves each carry their own particular loads, which then transfer it through stresses. So what part of the bridge might handle bending stresses?
just the road itself.
Right, the road, the beams. So these would be like beams. Pretty straightforward, right? We'll learn about how to calculate all of these later on in the semester, but today we are going to be focusing on axial loading and stresses. Some of these problems get a little confusing, but don't worry. So let's consider an example. Let's say we've got a beam here. But instead of it being like a beam, it's just some vertical element. And it's subjected to some load. Somebody pick the magnitude of the force. How large do you guys want this to be? 10 kips? All right. Great. Now, let's pick some geometric properties about it. Let's say that when we look at this from a cross-sectional perspective, so looking at it from the section AA, it's rectangular in cross-section, and it's 12 inches by 12 inches. All right? Now, let's determine the stress. But right before we do that, let's just define really quickly some of these variables. Stress, we commonly refer to as this Greek letter. It's basically a zero with a hat. My students last semester got really creative and did not call them the appropriate names. So this term is called sigma. The force is just going to equal F, and then the area is just A. All right, so if we wanted to calculate the stress in this member, how would we do that? All right, we've got 10 kips,
144.
and then 144 square inches. Because the area is 12 by 12, so 12 times 12 is 144. What do we get for the stress? We get 0.07, and we'll use units of KSI. This represents some, whoops, that's way too large. Kips per inches squared. Do the units look familiar at all? KSI, we could convert this to PSI, right? How do we do that? How many pounds are in a kip? 1,000 pounds in a kip. So if we were to convert this to PSI, just multiply it by 1,000. And you would get, I did some rounding off, but the actual value would be like 69.4 PSI, which rounds up to about 70 PSI. So it's a very small stress. We can also convert this to units of PSF. How many square feet are in a square inch? Well, here's a nice little trick. If we wanted to convert it to PSF, you can just multiply it by 1, or no. There's 12 inches squared per foot squared. Let me actually like move this like way up here. So multiply it by 12 inches per foot, and then just square the whole thing. And what you guys will notice is the inches and the inches will cancel out. And what we would get for stress at this point now is 10,000 pounds per square foot. Let me increase the size of this slightly. So let me ask you this. Which stress is the correct stress? You want to take a crack at it? Which one's the correct stress?
I guess it would, all of them, right?
Yeah, exactly. They're all the same terms of units. But this is where it's really important to pay attention to units. Because if you write down that it's 10 kips per square inch and you're designing something for 10 kips per square foot, there's going to be a big issue because you're not paying attention to your units. So this course really emphasizes the use of units, which is probably the number one thing that students got wrong last semester. So always pay mind to the units, because when we start getting into comparison of material properties, for example, all material properties are going to be given to you in units. Has anyone heard of the American Society for Testing and Materials, ASTM? Yeah, some people. This professional organization has conducted tests on a ton of different materials. So there's always going to be material properties that we know for select materials. And these materials are always going to have the material properties in terms of stresses because it's a normalized thing. Whereas, like, depending on the size of the material, it'll carry different forces, but the stresses will always be the same. Make sense? All right. Now let's get into this a little bit further. Let's say now we've got I'm going to get a little artistic with my drawings. I apologize if they take me a little bit of time to draw up, but I promise you they will be. I just deleted everything. There we go. Let's say now we've got a member loaded right here. And let's say it's about 1,000 pounds. And it's located ten inches away. And its cross section, I'm going to use BB actually. Is now just circular. And it has a diameter of, let's say, 3 inches. what would the stress be in this case? How about you guys give it a quick crack at what the stress would be? So 1,000 pound force divided by what? What's the area going to be? What's the area of a circle? Pi r squared. You can rewrite this in terms of diameter. This is my preferred. Pi over 4d squared. Which, when you calculate this, you're going to get roughly 7.07 inches squared. So when you throw this in there, you should get that the stress is equal. Oops. Oh, goodness. There we go. To 141.5 psi. Now, here's an important question. Is that entire rod stressed? Like, is every part of this rod going to feel this 1,000 pound force? I'm gonna trip myself over that. What do you guys think? Raise your hand if you think yes. You think every part is loaded. You think every part is loaded. You do. Who else? Who here says no? 1, 2, 3, 4, 5, 6. Who here doesn't give a crap? Does anyone happen to have a rubber band by any chance? You do? Who does? Nicole has a rubber band? Do you mind if I borrow? Oh, wait, here's one right here. All right, I'm gonna stand really close in the middle. So I hold both ends and I load it, right? Both sides stretch, right? Makes sense that the entire thing is fully under load, right? Now let's say I grab it at midpoint here and then I pull it. What about this part here that's a little floppy? Is that under any loading? It's unstressed. So in cases like this, it's really important to understand where loading is really occurring. So the stress is really only being felt in this region of the rod here. And then everything here is just freely translating because of this deformation. A way that we can do this is by drawing what we call internal force diagrams. These things can get very complicated very quickly once you start adding more and more load. So what we do is we say sum of the forces in the x direction equals 0. We'll call this a, what's a good color? Orange. This reaction is just going to be R. We'll have R plus 1,000 pounds. And what we get is R is equal to negative 1,000 pounds. So the reaction is actually moving to the left. Make sense so far? Great. Now, to get these diagrams, we need to observe how the forces look internally, because stress is dependent on what the internal forces are. Do you guys remember when you were dealing with trusses, you would do this thing called the method of sections, which you would cut into the members and analyze the forces internally? Do you guys remember that? You do the same exact thing here. So let's say we cut just an arbitrary section just right through there. Let me draw that down here. And then what was the rule with method of sections? You observe everything either to the left or to the right of the section that we're interested in, right? So in this case, our section is just going to be just like that, with the green line just coming down like that. Next, we draw our forces that are applied, which in this case is just going to be 1,000 pounds acting to the left. You guys see that so far? And the last thing that we do is we replace whatever material is remaining with our internal force, which I like to use the letter N for internal forces. So that would then in turn change this to N. So we look at forces in the x direction equals 0. And what's our equation going to be? It's going to be negative 1,000 pounds plus N. And N, you get positive 1,000 pounds. What does the positive indicate within the member? What do you guys remember from method of sections for trusses? What does a positive sign indicate?
Compression.
Wrong. Tension. So our rod is in tension, which makes sense because this load here is just pulling it out, right? Like this would get ripped right out of the wall if it was like not bonded properly. You guys would agree, right? I know it seems very easy right now, but once I throw 4 or 5 loads of different magnitudes, this thing gets complicated really quickly. And then you can't tell what part of what rod is under compression, which one's under tension. Which is why I'm telling you, just cut sections whenever you can, because it helps big time with understanding what the internal forces in each part of the rod are. Now, just for clarity's sake, let's cut a blue section right there. What our shape is going to then look like is it's just going to be a little bit longer. Our force is going to be 1,000 pounds. Let's draw the blue here. And then we include everything either to the left or to the right of the section. So in this case, we're going to have this 1,000 pound force added back. And then of course, we always add N. Let's just make things a little bit clearer here. And let's just say this part is A, or 1. Change that to 1. So we've got 0.1, 0.2, and 0.3. So that way now, this stress here, or the internal force, is N12, or the force within part 1,2, which would then make this the force in 0.23. What is N23 going to be? All right. Let's see if I can remember people's names. I know you're Michael, right? You're Grace? No, what's your name? Olivia? Yes, Olivia. There's not even a Grace out in this class. You're Nicole. I cheated a little bit because somebody said your name. What's your name? Ella. I don't think you were here last class, right? What's your name?
Alejandro.
Alejandro. You're Michael, I just said that. I cannot remember your name, I'm so sorry. What is
Emily.
it? Emily. I'm really bad with names, so I'm so sorry. What's your name?
Tom.
What is it?
Tom or Thomas.
Thomas. Your name?
Yeah.
Joe? No, Christian.
Isaac.
What is it?
Isaac.
As. And then
Edgar.
Edgar. All right. Nicole. What's force N23?
I'm sorry.
What's the internal force going to be? N23.
The internal force is 1,000 pounds.
Well, this is an externally applied force. So anything that you see drawn on the structures directly is always going to be an externally applied force. And the internal force is just the force that's not really going to be visible. Yeah.
Okay.
So what would N23 be?
Would we have to do the same thing we did with 1, 2?
Yeah.
Would we sum the forces
Same exact thing.
at the x?
Mm-hmm.
Okay. I'm still answering the question. Oh, okay.
Mhm.
Okay, so this one has another 1,000 pounds, so instead of it just being what it was before, would you have them both there,
Mm-hmm.
as in 1,000 pounds plus 1,000 pounds, or would it be negative?
One of them would be negative
Okay.
because they're moving in opposite directions.
Okay, okay. So it would be some of the forces at x equals 0, which equals negative 1,000 plus the positive 1,000
Mhm.
plus n,
N23.
2/3.
So then what would N23 be? 0. Remember what I was saying about the rubber bands? Grab this point here, pull it, the floppy part is not under any type of load. Same exact situation here, just of course if it was a steel rod, the visual would be much less noticeable. So, when we draw our diagrams now, we just draw like a little rectangle here because that stress is constant or the force is constant. And it's going to be positive 1,000 pounds and then 0. And then this in turn, once you divide it by the area, would be 141.5 psi. You guys agree?
Wait, how'd you figure out 141.5?
That comes from the stress that we computed up here. And so then, of course, like, really, this stress here, this force is not exactly the 1,000-pound force applied, but it's actually the internal force. So always use the internal force, because once you start seeing like 5 or 6 loads, then the stresses are dependent on how each load independently is affecting that section of material. Make sense? All right. I got a nice fun one now. Let's say now I've got a rod here. £1,000 force. That's still 1,000 pounds, don't worry, I'm just... £1,500 force. and then 500-pound force. And let's say that the location of each of these is just a third of the total length. So this will be like 5 inches, 5 inches, 5 inches. We'll call this point A, point B, point C, and point D. And what we want to determine is the stresses in AB, BC, CD. You guys agree there's 3 separate parts of this bar, right? How do you guys think we would determine the stresses? Or the forces, better yet. The first step we would always take is just determine external equilibrium. This is your sum of the forces, sum of the moments. It's your statics. So what we're going to have now is our reaction force, RA. And what would the sum of the forces in the x direction equal? Let's say we want to determine RA. What would that be? Is it a perpendicular distance or parallel? So here's the nice thing about uniaxial loads is you're never going to have to take moments with these types of loads. All right? Once we get into beam theory and beam stresses, yes, you will need to take moments. But as of right now, everything is just purely axial loads. So you shouldn't need to multiply force times distance. Yeah.
1,000 minus 1,500 plus 500.
What's the missing link? Not quite. Plus RA. Because remember, we're solving for external equilibrium. External. Our value n that we had previously was internal. So always ignore internal when you're doing this external equilibrium step. So you solve for RA. What do you guys get? What do you get? 0. See where things get confusing now? You have all of these forces. How is the reaction at the end 0? Starts getting complicated, right? This is a fun problem. All right. Step 2. Now we look at internal equilibrium. All right. And this is the step where you start cutting into sections. So, how many sections are we going to want to cut here? 3. My recommendation is just always cut them right down the middle of each. So we're going to have section 1, section 2, and section 3. Always including everything to either the left or to the right of said section. So looking at section 1, what are we going to have? It's just going to be this rectangular section right here. And then we would generally draw RA but we know that that's 0. And we're going to have our internal force NAB this time, because of the points it's between, NAB. You can also, if you wanted to, say it's N1. Doesn't matter. You could say it's either the stress in between the points A and B or the stress at section cut 1. Doesn't really matter too much how you call it, just as long as it's correct. So, what's the stress in that region of rod? Or the force? Is it 1,000?
0.
0. You notice that. You got caught up there. You saw the 1,000-pound force, and you thought that it was in 1,000 pounds, but it's 0. Because when you do sum of the forces in the x and the y direction, well, y direction is just 0, but the x direction is 1,000. So all of these forces here and here, too, are contributing to the total reaction force here, and in turn affecting the stresses within A and B. So, simply put, the force in member AB, or part AB, is just 0. Let's look at section 2 now. All right. Our force here is going to be 1,000-pound force moving to the left. And now we draw NBC, or N2. What's that tell us about member BC? Keep in mind, you guys notice the direction that I'm drawing the forces? It's always away from the cut section, indicating it's assuming tension. So we're assuming that the internal force here is in tension. How do we determine its magnitude? What do you guys think? Emily?
Would be, if F by X equals 0.
Yeah. Just apply your statics, just it's internal this time. So you do sum of the forces in the x direction, set that equal to 0. And what's that equation going to look like?
1,000 plus NBC.
Yeah. So we've got 1,000-pound force plus NBC. And what's NBC going to be?
Negative 1,000.
Mm-hmm. What does the negative sign indicate?
Compression.
Compression. Who the heck said tension?
Oh, I did. Okay.
So 1,000-pound force in compression. Last step, look at the section cut 3. It's kind of long, I know. And then our internal force NCD or N3. that should be an arrow. What's NCD going to be now? Michael.
So you would do, wouldn't we just do the same thing as the last one?
Yeah, which is
The
what?
sum of force of x?
Mm-hmm. What's that equation going to look like?
It would be 1,000 plus negative 1,500 plus NCD.
What do we get for NCD? Did you say it?
Negative 500.
It's positive 500.
Positive 500.
Carry the 500 over. That's going to be in tension. Another way you could have done this is we could have looked at the section from the exact opposite way. So I'll just show like an example of how that's done. So here, it would be a 500-pound force. Our section would be here, and then our internal force would just, again, be in tension. And what you find from forces in x direction is negative NCD plus 500. NCD is 500 pounds in tension. So you guys see that as long as you're doing your steps correctly, it doesn't really matter which side you take the section from. As long as everything that you did up to this point is correct, your math should work out. 500 pounds and 500 pounds, they should match. Make sense so far? Sweet. So now we go over to draw our internal force diagrams. And then I'm just going to mark this out really quickly. We've got point A, point B, point C, and then point D. What is the magnitude of the force in member AB? 0. So we could just put a little 0 right there. What about the magnitude of the force in member BC?
1,000.
Compression or tension?
Compression.
Compression. So make sure you add like a little negative sign. I usually like drawing it in red. And then CD is what? Positive 500 in tension, right? So you just draw that little diagram here. I'm trying to do it to scale. Positive 500-pound force. And that's how that member is really loaded. You notice there's a 1,500-pound applied force, but really with the contribution of all the forces, we only need to really design for an internal force of 1,000 pounds. Now you understand why how the loads kind of transfer down in a building, right? The columns can actually be a lot smaller towards the top of the building because of the fact that there's a lot less load. So it's just, instead of it being left and right, it's just you're stacking downward force by downward force by downward force by downward force. And you can draw these diagrams for the buildings accordingly. Make sense? Sweet. All right. Let's complicate things even more now. Let's say, let me actually ask this. Does anyone have any questions so far about anything that I just covered? Nobody? No questions at all? I just wanna make sure everyone's fully understanding it before I start throwing more stuff at it. All good? Cool. Coolio. Let's say now we have a rod, but it's a stepped rod. And we apply this force here. I gotta turn that thing off. And this is about 10 kips. Now let's say that this is a circular shaft with a diameter of around 4 inches. And then this is a shaft with a diameter of, let's say, 2 inches. Just so you guys have this information, I'll give you guys the lengths too. So this is going to be 10 inches. This we'll say is 8 inches. And then I just realized I never even gave you guys geometric properties for the previous problem, but that's fine. It's the same steps. You would just take each independent force, just divide it by the area. Let's say we wanted to determine the stresses now for AB and BC. So that's A, B, and BC. What's step 1 of this problem? Exactly. Step 1 is just external equilibrium. What do we get for the reaction at A? You do sum of the forces in the x direction. We get RA plus 10 kips, right? Indicating that RA is equal to negative 10 kips or just 10 kips moving to the left. Everyone see that? Great. Now, what's the internal force in member AB? Yeah.
Sorry, quick question. It's negative 10? If it's moving to the right, would it
You draw it assuming it's always moving to the right, and then mathematically, since this is moving to the right, this has to move to the left. So you would get RA plus 10, this becomes negative 10, and the negative sign just indicates that the assumption you made here about the direction is incorrect.
Okay.
All right? So just really quickly, what's the internal force in member AB? Cut a quick section, see it in your mind, or draw it out on your paper. What do you guys see the internal force as? Yeah. Not quite. If you were to cut a section, just like this, and then just ignore everything to the right in that section. What's the internal force of it? What is it? Somebody said it. It's 10 kips. What about for member BC? What's the internal force for member BC? Still 10 kips. So it's safe to say that this whole rod is just feeling the 10 kip load, right? And it's pretty easy to kind of see that because this is just 10 kips, and this 10 kips is just going to be felt throughout the entire length of the rod because there's no other applied forces to kind of cause confusion. So, just from observation, when you go to step 2 and conduct internal equilibrium, you can just say all internal forces equal 10 kips. Now, that 10 kips that you guys were calling out, is that a tension or a compression force? Compression?
Tension.
It's a tension force. So it's 10 kips in tension. Great. Now, step 3 of the problem, we didn't do it for the previous problem, but we're going to do it for this one. Determine stresses. So we're going to have one for AB and one for BC. What do we need to compute the stress? Remember our stress equation. I want somebody back here. But Michael, you get to pick one of the 3 back here. Please announce your name again. You're Joe, Christian, and
Irving.
what is it?
Irving.
Irving. So you get 3 options: Joe, Christian, or Irving. You get to ruin one of their afternoons or evenings.
I'll just do Christian.
Christian. Yeah. What do we need to determine the stresses?
Stress equation.
Yeah. And what does the stress equation tell us?
Stress equals to force.
Force over area. We have the force. So what else do we need? We need the area. How do we determine the area here? What are we given?
Diameter.
The diameter. And what's the equation for using a diameter? The diameter indicates it's a circle, so what's the equation? Pi over 4d squared. Exactly. So the area here, pi over 4 times the diameter, which is going to be 4 inches squared. Which gives us an area of around 12.57 square inches. Let's do it really quickly for BC. And the area is 3.14 inches squared. The stress is just going to be 10 kips divided by 12.57 inches squared. And that gives us roughly 0.80 KSI. For the other shape, it's going to be 3.18 KSI. Give or take. Yeah. What do you guys notice about the stresses? .18 and 0.80. How does that make sense? This is only twice the diameter. But the stress is 4 times the size. What do you guys think? Say that again?
Is there a movement on it from RA?
No moment. We didn't take any moments. What did you say? Say it.
Value,
Yeah, but what about the value specifically? Well, the reason being is because AB is 4 times the area, even though it's only twice the diameter. So because of that, it takes a quarter of the load, right? Does that make sense? So this is where it's really important to make sure that your area equations are right, and why it's also kind of important to have this normalized value of stress. Because let's say that we were designing something with an allowable stress of around 2 kips per square inch. Would AB fail if the strength of the material is 2 kips per square inch? I would say no, because we're only reaching about 0.80 kips per square inch, which means we have about 1.2 kips per square inch of leeway, right? You guys would agree with me with that? We could load it a bit more. What about BC? Would it fail? Yeah, because it's exceeding what the material can handle. All right. We'll give you guys a few minutes of break. Let's come back at like 7:10, 7:15-ish. All right? Cool. What?
I have a question on that cover.
All right.
I was able to do like all the other questions. I was kind of struggling like where to start with like the distributed load. Because I know 15,000 you do times the 8,
Yeah.
but I don't know what would you do with this 12?
So with the distributed load, you multiply it by the entire length. So it's,
we're by both of these.
yeah, it's a rectangular load. So when it comes to a rectangularly distributed load, nice way of drawing it is just simply like this. Its height, you can think of it like 1,200. Just this time now, it's got units. What's its total length?
It's 19 feet 6 inches.
So 19.5 feet. And where's the center of this load?
But 8 feet.
Not quite.
Oh wait.
It's 19.5 divided by 2.
So that would be 9.75.
Yep, so 9.75 is your moment arm.
Okay.
Total magnitude is the area. So what's 1,200 times 19.5?
23,400.
This is your equivalent system. Now, pay close attention to what I said about the problem too. I give you guys diagrams and ask you to account for the self-weight of the beam. What size beam was it?
Not
Well, I'll tell you here. It's the beam was a W12 by 40, I believe. What do you guys remember about a W12 by 40? What does that mean? What do the two numbers mean?
The length is 12, and then the weight is like the linear square, like how much
Isn't the
weight is
depth
in the
40?
linear square foot.
Say we've got a W shape, looks just like this. It's kind of like a W shape, right? We would take, flange and web might be way too thick, but that's perfectly fine. I don't feel like going to Professor Simon's classroom and carrying like a 60-pound member of steel to bring to you guys and then have to lug it all the way back. So we'll just have to make do with this. W12 by 40. The first dimension is just an approximation, we call it D. If you look at like steel tables or look up on the internet, for a W12 by 40, the depth is approximately 12 inches. But I think the exact height is 11.7 inches, if I'm not mistaken.
It's 11.8.
It's 11.8?
I don't know.
Ah.
Yeah, I don't know the textbook by heart.
Yeah, let's look it up real quick. Oh, I was looking up trading cards for flights. Don't worry about that. I just realized that United Airlines does that. 12 by 40 dimensions. It has a depth of 11.9 inches.
I was closer.
Yeah, you were closer. So its depth is 11.9 inches. And then what's the 40 mean? You were right on the money with it. What does it mean?
It's like the weight per linear square foot or something.
Just per linear foot.
Yeah, whatever it is.
Yeah, so the important part for that, when you're accounting for the self-weight, just throw 40 there.
You multiply, right?
Nope, just add it.
Oh.
Add it in, and then instead of this being 23,400, it'll just be whatever the updated value is from 12,040 times 19.5 feet. Make sense?
And then you would just add that on to the 15,000 times 8.
Mm-hmm.
Okay,
Yeah.
that makes sense.
Usually you don't even bother dealing with the self-weight, but if you're like trying to really save on money, then if your factor of safety you're getting at like 1.01 or whatever, trying to save money, then that weight you really want to account for, because even if you're a fraction off, the self-weight can actually cause the building to collapse. Make sense?
Yeah, and then number 4, do you want us to find the inertia also? That's the
I believe so.
centroid question.
What did the question say on the homework?
Let me go back.
Let me look it up. COT, semesters, fall 2025. Let me not pull up the solutions. Oh, that's homework 2. That's next. Locate the XX centroid and compute the second moment area of inertia. So that's the I value, second moment
Is
area.
that I of X or is that the I of
I of X, yeah. Yeah, I specify about the XX centroid, which is going to be wherever the neutral axis is.
Yeah. Alright, thank you.
Yep. Where is this? Let me just check this really quickly. give you guys a little bit of a fun problem. I'm gonna teach you guys a little bit about how to design stuff now. All right, since we learned how to analyze internal forces, we understand the concept of stresses, hopefully, right? All right, so this problem I'm giving you guys now, I give you guys an allowable stress of 36 kips per square inch. What this means is that it's a material property. This is a new concept to you guys also. 36 KSI, for your knowledge, is the typical yield strength, we call it, we'll get into it later on, for A36 steel, which is a type of steel that is heavily used in the construction industry. A lot of steel members, like steel channels, steel angles, are made from A36 steel, and its allowable stress is 36 KSI. So, my question to you guys is, what is the diameter that we would need in order for it to not fail? And let's round it to the nearest 16th of an inch, right? Because if you went to a fabricator and you were like, I need a steel member with a circular diameter of 2.84193678 inches in diameter, the contractor would more than likely smack you over the head with that steel member, right? Round it up. So, step one. What's step one of our problem? External EQ. Simply put, we're just going to have this reaction force. The reaction is just going to be 100 kips. Moving to the right. What's step two? Internal equilibrium. Simply put, the entire force N is just going to be 100 kips. And if you look closely enough, you'll notice it's going to be in tension. I made the loading very simple so that way we could just skip straight over to the design. Step three. What was step three? Determine the stresses. But what's the issue?
We need the diameter, which we don't have to.
Yeah, we're figuring out what the diameter is. So, we got to do a little bit of manipulation. So step three in this case, instead of determining stresses, let's say determine the diameter. So it's really determine whatever thing you need to solve for stress problems. So in this case, our equation for stress is equal to what? What was stress equal to? Force over area, N over A. What two things do we know? We know the allowable stress of the material. So it could be safe to assume that we can just add the allow here and just say, let the stress be 36 KSI, right? What else do we know? Yeah,
We know
the internal force. Yeah. So we can just rewrite this entire expression to find the area, which when you cross multiply, it's just going to be the internal force divided by the allowable stress. So take that 100 kips, divide it by 36 kips per square inch, or KSI. What we notice is the kips will cancel, and then what you're left with is 1 over inches squared. And what you guys notice, if you guys remember from like your math classes in high school, when you have a fraction of a fraction, just take this denominator, throw it up on the top. So our units will be in inches squared. So our area becomes 2.78 inches squared. Now, go to a contractor and tell him I need a steel rod, circular in diameter, with an area of 2.78 inches squared. He's going to be like, just give me a dang diameter. He's like, what am I trying to do? So, how do we determine the diameter of the rod now? We have the area. What was your name again? What is it? Aza. For some reason, I thought I heard Anna, but then I was like, no, I think it's Aza. I wasn't sure. Ada.
Yeah.
Aza, though, right? It's, how do you spell it? Easy A. So, okay, pretty easy spelling that. I have no excuse to mess that up again. Aza. What would you do? How would you determine the diameter?
From the area, the field code, and so we're looking for the diameter, so we can find from the variable, like P over 4,
Mm-hmm.
diameter.
Yeah, so we could use that area equation, right? So we know that the area for a circle is pi over 4 times the diameter squared. So we can just set this equal to that 2.78 inches squared. Let's break this down a bit more. Multiply both sides by 4 over pi. The pi over 4s will cancel with the 4 over pi. So what we're left with is d squared is equal to 2.78 times 4 over pi. What we can do now is just take a square root of both sides. And what we get is d is equal to whatever the area is times 4, or 4 times the area divided by pi. Whoops. 4 times 2. What do we get for the diameter? We get 1.881 inches. So, now let's round it to the nearest 16th of an inch. What diameter would work? What do you guys think? Should I make it 1/8 of an inch? 16ths might be a little small or annoying. We know that we need a diameter of 1.881 inches. What's the nearest 16th of an inch measurement of that?
$1.875.
You just killed everyone in the building. It's smaller than the required diameter. But you're close, yes.
Oh, right there. I was
Mhm.
thinking about it not going over the allowable. I
Right.
confused those two.
But here's the thing, when it comes to the diameter, always just increase the diameter.
Okay.
So you were technically correct that it's the nearest 16th of an inch,
Just kill them.
but you gotta go the opposite direction. So, just take that 1.875 inches and just add 1/16 of an inch. So that's going to be like 1.9375, which that's 1 and 15/16 of an inch. So we would be safe in saying all right. Make sense why we go up instead of down? Yeah.
What did you get that?
So the nearest 16th of an inch value is going to be 1 7/8. What that is in terms of decimal units is 1.875. However, 1.875 is too small because we need at least 1.881. So you just add an additional 16th of an inch to that 1 7/8, and what you get is 1 15/16. Now in practice, the contractor would throw the 1 15/16 inch bolt over at you because you would be like, just use a 2-inch diameter bolt. It's a lot easier. So, in practical uses, just round up to a 2-inch bolt. Any questions about that? No? Cool. Let's now consider another problem now. Let's say that this has an unknown diameter, and then this is rectangular with unknown dimensions of B. Let's say that this force is 10 kips, and then this here is 5 kips. And then dimensions of 8 inches and 8 inches. And this material has an allowable stress of 50 KSI. And we'll just say that this is a typical stress. So all the material is the same in this problem. All right. What we want to do is size out each of the members. What do you guys think we would do? Remember your steps. I'm going to keep drilling these steps into your skulls until you're repeating them like Professor Dawson's clear as mud expression. Does he still say that?
Yeah.
He does?
Yeah.
I hate that expression, but I love it at the same time. Because he used to always look at me and be like, clear as mud? And I'd just look at him in straight confusion. Like, I got no clue what you're talking about, but okay. Yeah, when I took his first statics course, the non-engineering one, I failed that. I was not good at statics. So I always thought he was targeting me when he said clear as mud. All right. So, step 1. Hopefully you guys know the drill by now. What's step 1? External equilibrium. All right. Our reaction force is going to be right over here. And let's label A, B, and C. So this is going to be AX. Let's do sum of the forces in the x direction. What's our equation going to be? Yeah.
AX plus 5 kips.
Who here agrees? Let me zoom in a bit. Might help. Plus 10 minus 5 kips. What do we get for AX? Somebody tell me that. I'm too lazy to throw it into my calculator. Negative 5 kips. So it just means that it's 5 kips moving to the left. So I'm just going to erase that really quickly and just actually let me just redraw it as that and just cross that out. Step 2, internal equilibrium. All right. How many internal forces are we going to have?
It's 2, right?
2. Yep. We're going to have an internal force AB and an internal force BC. So let's look at AB really quickly. Oh, yikes. We've got AB. We've got our internal force NAB. And then we've got our reaction force of 5 kips. From observation, what do we get NAB equal to? What is it? Not negative. It's positive. Let's do sum of the forces in the x direction. We get negative 5 kips plus NAB, right? So then you just carry the negative 5 over and you get positive 5 kips. What does the positive indicate? Tension. Awesome. Am I going too fast, by the way, or am I going good? Sweet. Let's do BC now. Darn math assistant. I don't need assistant with my math. My math is suck. All right. We've got 5 kips going to the left, reaction force. And now 10 kips going to the right. But I drew this really poorly. So let me try and capture this in as good a detail as possible. So we've got 10 kips. And then our reaction, internal reaction, NBC. Let's do sum of the forces in the x direction. What's that gonna look like?
Negative 5 plus 10
-5 plus 10
plus
NBC.
NBC.
What do we get NBC is equal to? Negative 5 kips. What's the negative indicate? Compression. So instead of just drawing the diagram, I am just going to just put NAB is equal to positive 5 kips NBC is equal to -5 kips. And let's just box that for now. All right. Now, let's go over to step 3. What's step 3 gonna be?
Determine the diameter.
Determine geometric properties, because if you guys pay close attention to BC, it's not a circle. Determine geometries. All right, so remember our equation, sigma is equal to n over a. We can rewrite this to then just say that the area is equal to force over the allowable stress. And we look at AB, just real quick. The area is going to be the internal force, which is our +5 kips. And then the allowable stress was 50 kips per square inch, which is going to be 0.1 inches squared. We look at BC, and our area we compute is going to be -5 kips divided by 50 KSI. And what you get is technically 0.1 inches squared, but negative. Can we have a negative area? No. So this allowable stress, we usually just put a negative sign because the stress doesn't matter if it's tension or compression, it can handle the same value. It's just it's going to be on the opposite side of the loading. So it can handle 50 kips per square inch of negative compression. So negatives cancel, which gives you the area that you're looking for. So just whenever you get an area, if you're getting a negative value, chances are just remove the negative sign. Make sense? All right. So we know that we need at least an area of 0.1 inches squared for both elements. So for AB, how would we determine what diameter would we need to get that area? How would we do that? Actually, you guys try it by yourselves. I want to see what you guys come up with. And then I'll cross compare. And once you got something, just raise your hand. for the circle, that looks right.
Okay.
Yeah.
Am I rounding this again like last time?
No, no need.
Okay.
If you were designing something, I'd be like, yeah, round it.
How did you like round it again? So you just like
When it comes to like rounding, you just gotta get used to like all of the numbers. So,
Yeah.
but you just pick whatever 1/16 of an inch or 1/8 of an inch is closest.
so I think
So in this case, that's 5/16. 6/16 would be 0.375. So 6/16 would be 3/8. So 3/8 would be the best bet because you can't use 5/16 because that's too small.
right.
So 3/8 would be the size that you would want to use. for
Okay.
that. Make sense?
Yeah, that makes sense. Thank you.
It's just a matter of plugging in the values over and over again.
Gotcha.
If you know your 1/16 inch
Mhm.
values, increments, it gets easier.
All right.
Is this hard?
It is not. So, let's see your calculator. So 0.1 divided by 4. So here's where the issues come in. The way that these calculators work is it's taking 0.1 and dividing it by pi, and then it's dividing that whole thing and then by 4.
Oh.
Which, what you want to do is that. And that should be divided by pi, which then you square root that.
Should I bring my fancier calculator next time so I don't have to?
Probably, yeah. I like to,
I have a better one.
I like to use like this one. You could get these at like, off like Amazon, I think for like $10. But they're like really nice. But, yeah, so you have that 0.1 multiplied by 4. Oops. 0.1 times 4, divide that by pi. And then you just take the square root of that answer, and that's your diameter.
Okay.
But yeah, you can bring your calculator to, what is it, a TI-84, I guess?
The expensive one.
What?
Whichever one I spend a lot of money on.
It's probably that one, I don't know. Yeah, the TI-84s are outrageously expensive. Yeah, I have to take my PE exam, we're not allowed to use those calculators. It's this.
Oh, are we allowed to use those ones for our exams or?
Yeah, you can use whatever calculators, just not your phones. I've had bad experiences. Students using ChatGPT during the exam. And then I'm like, don't do that, they'll get the problem wrong. Yeah, let's see. So,
So you get that in the,
yeah, that's your diameter.
just for one.
Yeah, now you, this one I said was a rectangular shape or square, so it's just gonna be 0.1 converted into square units.
Thank you.
Mm-hmm. With the geometry over here. That looks good. Yeah, that would be great. Alright, yeah, it looks good. Let's do it. Let me just check over here. How's it coming over here? You see? That looks good. I don't think you're accounting for the pi and the square root. Yes. All right, let's do this real quick, and then I'll give you guys what I like to call get out of jail. It's basically just two problems that I'm going to be asking you guys to solve. They don't count towards anything, but I take them home, I review them, and then I just comment about some stuff that you guys did wrong. So it just helps me assess like whether you guys are learning the material or not. All right, so area of a circle. Let's do the circle first, AB. The area of the circle is pi over 4 d squared. We saw in the previous problem, we could rewrite this to then just be d is equal to 4a over pi, which then is just going to be 4 times 0.1 inches squared divided by pi, which, if you do this correctly, should give you 0.357 inches. And that's the diameter of rod AB. Now for BC, I gave you guys dimensions of B times B. What this indicates is it's actually a square. And what do we know about the area of a square? Length times width, right? So this is going to be B times B. So what is the area going to be? B squared, right? B times B, which is equal to B squared. We set that equal to 0.1 inches squared. And so B is just going to be the square root of 0.1. And what we get is that the dimension should be 0.316 inches. Let me just draw a circle here. And those are the dimensions that you would need and how you would size out the members. Make sense to everyone? Are there any questions? Let everyone finish writing. Class ends at 8:15, so you guys should have half an hour to do these. But once you finish them and feel comfortable with them, you guys can leave. Just try both of them, all right? Just give each one a try. All right? Like I said, don't feel pressured. I'm not grading them. They're more so for me to make sure that I'm teaching properly. And you guys can ask me like questions and such, just like the previous problem. It's just full length problems now for you guys to try. I also did not generate a solution for these at all, so I'm probably going to do that real quick right now. And you guys can work together too on it. Like I don't mind. This is just for you guys to, yeah. Alright, everyone done? Kidding, I'm just busting your chops.